Is everybody familiar with what locum is? I'm going to guess no. Okay, so let's talk about that. Did everybody get a chance to see this? Do I need to pass this around before I put it in the fire? You didn't see it? Okay, let's pass this around real quick, but then I'll need to get it in the furnace. And I'll explain what that is. So what you see there is a laminated block of copper, brass, in this case a red brass, and nickel silver. And that has been already bonded together in a manner that's very similar to the forge welding process that we would use to do pattern welded steel, except that it's not done with deformation, where when we do a pattern welded piece, we have a big stack and we smash it under a press or a hammer and everything sticks together and we've kept it clean. What's done to make that is you start with much thinner layers. So sheet metal, which has been sheared to the desired sizes, that sheet metal is then cleaned very meticulously, often pickled, and then it's held with gloves. And then it's stacked up in whatever the arrangement is that the gentleman who's provided that did. And then that's wrapped up in a stainless steel heat treat foil. It's squeezed between two steel plates with bolts on the corners, and then that's placed into an electric kiln. And the clean surface and the pressure from the plates is sufficient to get bonding of those layers, but they have to be really, really clean. So a block like that one, which started off with 2x2 by 6 was the original dimensions. It's been machined on the sides just to remove the uneven surfaces. So that block, often we would present those to me at, like, say, with 88 layers as a common layer count for what he does. So I should back up just a moment. I did not make that block. That was provided by a gentleman named Mike Sackmar. I do a lot of forging for Mike. He makes blocks like that. He sends them to me, and then I forge them into the sizes that he needs. That's been really the only paying work I do in my blacksmith shop for the most part for probably the last 12 or 13 years. And Mike has very graciously donated several pieces to the auction, which are out on display and available for auction tonight, that have already been machined and are free of any surface imperfection. The forgings that I make today, that block will go back to Mike so that he can put that back in his inventory. But once he's done with his, I'm going to call it bonding. Some people would call it fusing, but there's no melting happening, so you're not really melting anything. But bonding is happening during the time in the furnace. Then you remove it from the furnace, you disassemble the little compression plates, unwrap the foil, and then clean up the surfaces either through grinding or milling, as in this case. And so at that point, you have a block that's ready to be forged. Is everybody still here? I want to make sure. Okay. At that point, you have a block that's ready to be forged. Blocks can be made in different sizes. A very common size for Mike to produce is that 2x2 by 6, but he's done larger ones. And the size that he produces is really dictated by what his customer wants to receive, or how we want to plan forging of the parts, and how can we get the best yield of material. Because they're copper alloys, so they're not as expensive as gold and silver, but they're certainly not cheap. So how do we maximize yield? And this gets into another aspect of that control I was talking about this morning. How do we control our process? So in this case, one of the ways that we can control process is by selecting a size that's going to give us the minimum amount of waste. In this type of product, waste is usually at the very ends, where you have your tong holes. We'll be doing some twisting, so I'll have the twisting wrench, I have to grab there, and that part that I'm grabbing, of course, won't be twisted. But also what happens when you are forging a laminated block in the way that I'm going to forge this one, the ends will push out the head of the center. And so I'll try to do another sketch to illustrate this. But you'll see it as we go along, but I'm going to try to give you advanced view. Actually, I'm going to leave this here for drawing and then show it. So, you start with a block. The block has this sort of shape, and we have stripes. Like so. And if I really want to get fancy, we'll shade in every other stripe so you can see the alternating materials. Okay, so we have this stripe thing down. When we forge this, the metal has to go somewhere, right? Because I'm not going to lose any volume, especially with this material. The oxidation is very minimal when you're doing this. It's going to be at a much lower temperature, and it's different materials, so it doesn't oxidize in the same manner that steel does. So we'll just assume that we're not going to lose any volume. What's going to happen is I'm going to forge this, and if I forge it correctly, this center section will move out in this direction faster than this surface. Okay? So what I'll end up with is a piece that's got a bulge on the end. This is true whether I have a straight laminated piece or just any other piece, some non-laminated material. If I'm forging with sufficient power, I'll push the center out ahead of the surface. In a laminated piece, what will happen as this becomes somewhat extreme is the layers which are closest to the surface will terminate before you get to the end of the piece. And this one comes down here like this. And you'll probably be able to see this as I forge that part, right? Now, so out here, so when I'm looking down, if I'm looking down on this, I will have my original top layer will be this one here. And then I will be able to see little stripes like this. And we'll have more and more of these as we get closer and closer to the end. This ends up becoming a pattern that looks a lot like a fingerprint. That fingerprint is going to be quite different in appearance than the rest of the part. We're going to twist this, so we'll end up with a candy stripe appearance down here. Up here we'll have this fingerprint. So Mike is a person who really likes things to be as consistent as possible. He takes a lot of pride in providing consistent materials to his customers. So he'll cut this off. He won't necessarily throw it away, especially if it's big enough. He'll keep that and sell it to somebody who only wants a small little part like that. But we're trying to maximize the amount of consistent, uniform pattern material here. So one of the things that we could do when we're setting up a job, yes, Bruce? That's all right. So Bruce is asking for the materials involved in that. There's actually three. There's copper, nickel, silver, and red brass. I don't actually know the hardness values for those things. This is not a material that would ever be used in any sort of an edge tooling application, right? These are all for aesthetic purposes. Oh, you had to ask me that. Mostly copper. Brass is typically copper and zinc, and so you have less zinc in the red brass than you have in a yellow brass. Nickel silver, I can't remember if it actually has nickel in it or not. I forget what other element they put in there to give it that silvery look. Peter might know. Peter, do you know what the alloy elements are for nickel silver? No? Okay. Well then it must not matter because Peter doesn't know. Yeah, we could look it up. If you could do a Google search and find it pretty quick. I don't have it committed to memory. Is that piece mated all the way around? Okay. And I want to make sure everybody gets a chance to see it, but I do want to get it before we go.
How much will the raw materials cost?
For a block like that?
2 by 2 by 6, yeah.
Oh. I don't honestly know. That's the nice thing about the position I'm in is my only job is not to ruin the piece. He takes on all that cost of buying the raw material. So I do actually have a big responsibility in not melting that piece or damaging it some other way. But I am insulated from that raw material cost, which I know is not insignificant, because what Mike does is he doesn't buy just enough for one. He buys 4x8 sheets and slices them up into little pieces and so on. So he actually has a pretty high investment initially when he's purchasing material. He might, did everyone get a chance to see it? So he might buy enough material for 4 months or 6 months, depending on what he expects his customers to order. I'm going to just start that off at the edge of the forge because we're still talking, and I don't want it to get too hot too fast. Yes. No, definitely not. So these are all copper alloys, and when you're doing it work like this, you need to respect the metal in the stack that has the lowest melting temperature. So in this particular case, that would be the red brass. So what I like to forge at for something like this is around 1650. That works pretty good. Yesterday, some of you were here, and I did a little test, not with the Mokame, but I took a piece of nickel aluminum bronze and I forged out a little leaf. Here, we can pass this around. It's not anything fancy, but it was just a good way for me to get a sense for this forge in this lighting environment and be comfortable with what I needed to see visually, since we're not using any kind of pyrometers or thermocouples or anything like that for this. So that's a technique I'll often use, is find a material that has a working temperature similar to the Mokame or even a little lower, and make sure that I don't melt this. If I don't melt this, then the forge is going to be safe to use for that. That was a really good question. I'm glad you asked that. Are there other questions? So back to my little discussion of how metal's going to move while we're forging. So I want to minimize the amount of loss due to this fingerprint pattern. So quite often we're in a situation where Mike will sell kind of wholesale amounts to some customers. And so if I may have a job to forge, say, I might supply maybe 60 pieces that are forged to say 230,000 thick, basically this dimension, this cross section, and maybe 30 inches long. Okay, so I could get one of those. Actually, I could get two of those from that brick that's 2 by 2 by 6. Mike can supply me 2 by 2 by 6, or Mike can take and saw that in half and give me 2 pieces, 1 by 2 by 6. And he's done it both ways. I can forge either dimension. My equipment doesn't matter to me whether I'm starting with that size or a smaller cross section. But if I'm forging as singles, 1 by 2 by 6, I'm going to have 4 ends like this. If I take a little larger cross section like this and I forge that down to an intermediate size and then cut it, I'll still have 4 ends, because I still will have some that I have to grip for twisting, but I won't have this feature happening on the end that was at the mid-length of the part. And so by doing that, I can preserve more material at consistent pattern than if we forged it all out from a larger cross-section. We're going to forge it from a larger cross-section because we're going to do two different things today. But when you're thinking about production and how to maximize yield on expensive materials, understanding how this metal is going to move and controlling that to your advantage is something you want to consider. Let's see. I had a question at the break about some of the tools and a good reference. And so I have a book with me. Bruce brought it up. I had meant to pass this around and I forgot this morning. This book, which I'll pass around, is a fantastic reference for tooling, for industrial type forging tooling. That book was written in the 1930s. It was written by an English gentleman who was a blacksmith in doing railroad repair work. And so you see all industrial types of products there rather than ornamental products. But what's really neat to see in that book is the planning that goes into making a part and figuring out what your starting stock should be, how you're going to work it, in which order of operations you're going to use to end up with in his case, some very complicated shapes when he was all done. So that book does a really nice job of illustrating the tools, some of them that I talked about this morning, and different ways of using them. That book is available for free online. It's old enough that it's in the public domain. There are booksellers who make hard copies available. I happen to like hard copies when I can get them, so that's what I have. The name of the book is A Blacksmith's Manual Illustrated. The author is J.W. Lillico, and Tinka has copies, I think, doesn't she?
You didn't tell me that, so I didn't bring extra copies.
I'm sorry, but you'll take orders, won't you? See? So that's a book. Another book that I'm going to pass around while this is warming up is a book that I really, really like for heat treatment. Now this is not a how do we heat treat steel A and B and so forth. Thank you. Peter has just supplied me with the composition for nickel silver. It's 50 to 80% copper, 5 to 30% nickel, and 10 to 35% zinc. Thank you. Oh, you're looking for your part?
Yeah.
It got passed around this morning as part of our registration.
What's it worth to you?
Oh, you and Dave are going to have to fight now. Thank you. That's good. So the heat treatment book I'm going to pass around is not a prescriptive book for here's steel X heat treated this way, steel Y heat treated this way. That is not what this book is. This book is giving you an understanding of why steel behaves the way it does. This book was originally written in 1935. The copy I'm passing around is a 1965 edition. This book is no longer in publication, but it's not that hard to find through used booksellers. I really, really, really like that book, so much that I require all my interns to read it while they are working with me. There are lots of other books that are out there, lots of metallurgy textbooks, but I find that one to be the best as an introductory book to concepts. It's by a guy named M.A. Grossman. That particular edition was edited shortly after his death by a fellow named Edgar Bain. Some of you may be familiar with a microstructure called bainite. It's something that some of the knife makers are interested in. That structure is named after Edgar Bain, who's on the cover of that book. He was the guy that first identified it under a microscope. And it was quite kind of one of those, a number of revolutionary things in the world of metallurgy was kind of beginning to understand that as a structure that could be developed and the properties that you can get out of it. So that one is called Principles of Heat Treatment. Any of the editions that you might find are going to be good. the 1965 edition has more information in it than the earlier editions do, but they're all excellent. And what I really like about it is in the early chapters, the author, instead of just giving you a chart or a graph and saying, here, this is what you need to know, he goes through a set of experiments and he shows you what you would see under a microscope for different experimental conditions, different compositions. And from that information, he then develops some of those charts and graphs that we find in metallurgy that are so common today. But most of the time, when someone goes to teach something about metallurgy, we start right away with charts and graphs, and that's not always the best approach for everybody, and so I really like his approach. Are there questions while this is warming up? Yes? Why did I switch forges? Okay, I did that because this forge that we were using this morning runs very, very hot. Really hot, which is fine for steel, particularly good for the pattern welding that I was, where I was not wanting that to come apart. It's much more difficult to get that forge to run at low temperatures, which is what I need for this material. So this one is a forced air forge. That one is a naturally aspirated Venturi forge, and we just have a bit more control on this one. Other questions? Yes. Then squeeze it? Yeah, so half-inch plate, half-inch steel plate. Well, it's a half-inch steel plate on the top and on the bottom, and then there's holes for like a half-inch bolts, and it's just torqued down. And Mike is so meticulous that he uses a torque wrench and keeps all the bolts torqued for the same torque every time he does the job. And I think he only uses the bolts once, because of course they're going to be heated up. He does his heating at something just over 1800 degrees Fahrenheit, I think, for the compositions that he's using. So your bolts oxidize and lose their strength, right? So it's kind of a throwaway item at that point. Yeah, but yeah, he's exceptionally meticulous with what he does.
So the pressure for bonding the metals, it just comes from bolts going
No.
Does he pressurize them before?
Before. Yeah, tighten the bolts up. Well, you do get some of that, but really what's happening is as long as the pieces are so clean and they're close enough that you begin to get bonding. So yes, you're going to get some expansion from heating. Yes. Yep. Yeah, but you're not getting any melting. There's no melting. It's close. Yes, it is close. I saw some other questions. Yes. So when I visited his shop, he was pickling these in battery acid and handling them with pickling in battery acid, rinsing in acetone, and handling it with gloves all the way through the rest of the process, so there was no fingerprints on the workpiece. Because a fingerprint would have enough contamination of that surface to prevent bonding with this. Now see, like when we do pattern weld steel, we don't care about that. We're going to be at a much higher temperature. We're going to be doing a lot of deformation, and so your fingerprint oils aren't going to be a problem on a piece of steel that you're bonding, but with this material it is. He does not. There is another technique for doing bokeh where you actually would solder the layers together, and so there you'd use a flux and you would work to draw the solder completely through the interface, and that's what would hold those together. I don't know how common that technique is anymore. It was something that definitely was a part of, I would say a part of the jewelry crafts. I've seen it in some of the books I have for jewelry work, but I don't have any personal experience with it, and I think that when properly done, this method is probably going to be a method that gives you more workability. So if you're making a billet and if you're going to forge and roll that down to make a strip to make a ring or something like that, this method is probably going to give you more opportunity for that without the layers coming apart. But we got some questions there. That's all that he's doing, is he's cranking down on the bolts, yes. Yep, yep. I don't know, I don't recall. I don't know if Diego ever told me, not sure. Yeah. More questions? Yes?
So he's providing the building, you're working into something he designs.
That's right.
And he machines it down.
Yes, yes. So the full progression of the process would be for me to forge it to whatever size. So he might say, I want a flat bar like this, or a bigger one, or an octagonal cross section, and then I would send that back to him, and he would machine it to a size to go to his customer. So he would typically take something like this, which is 230 thousandths of an inch thick, and machine that to 135. So basically sending it to his customer at 1/8 of an inch with a little bit over that. Yeah. I don't remember exactly, but your time is going to be a function of how big your billet is. Probably for something this size, I would guess it's 2 hours, but I don't actually know of that. This technique is quite different from maybe what you've seen, like people have experimented with quarters and getting quarters. You're doing the same kind of thing, but typically with quarters, you're using a torch or something and trying to heat them up. The bonding is still happening by the same metallurgy. I think quarters are probably harder to make successfully work than nice flat sheets. But I only tried the quarter method one time. My son was interested. He said, "Look, Dad, let's go do this." Well, okay, we'll try it. We didn't have nearly as much success with that as I've had with these.
Yeah, they were in my mind. I was thinking about packing half an hour.
Oh, it's been done. You absolutely can do it. But when you think about coins, they have those impressions, right? So they're not flat, and it's going to be harder to clean them. And also, you have much thinner layers in the silver layer on a $50 or a quarter than what we have to start with here. By the time we're done, the layers will get pretty thin.
Did you use silver quarter or anything modern quarter?
Oh, we just used modern stuff that he had in his wallet. Yeah, just the copper, silver clad ones. Yeah. We made some slight modifications to this forge yesterday because it's got a kind of a trough on the inside of it, so your workpieces all kind of want to drop down into that trough. And so we just put some random chunks of firework in there to take up that space, but needed to be adjusted a little bit for that. So we were talking earlier about controlling how metal moves, and I'm just trying to make sure I don't overheat this. So when we're forging, whether it be with a power hammer, a press, anvil and hand hammer, how we use the tools affects the way the metal's going to move. So if we hit with a hard blow or a soft blow, if we hit with a lot of contact area or a little bit of contact area, that all makes a difference to how the metal's going to behave. So if we want a specific outcome, we need to control that and be intentional about how we use our equipment. This is getting kind of close. We'll give it just a little bit longer. So what I want to do is I want to make this end bulge out a little bit. I don't want it to bulge out excessively because that will make this condition more severe. And when I create a bulge like this, there's a stretching action that's happening like this. There's a load, and this metal wants to stretch, and so that we end up putting the very center of our workpiece into tension. And we have an interface right here between layer 1 and layer 2. So if we have too much tension here, that can separate and create a defect in the workpiece. So but if I don't get a bulge, I could have something else happen that's undesirable. I can end up with sort of this kind of feature happening, where I've forged in a manner where the effect of the blow is penetrating only in the near surface region of the part, here, and not into the center, here. And so I end up with this bulging effect happening on either side of center instead of at the center. And that also is going to become a defect. So I don't want that to happen either. So I need to forge this in a way to get this, but not let it become severe. So we check the temperature one more time, and then we'll explain how we do that. All right, I think I'm going to go ahead and start. It might be a little bit cooler than it has to be, but I don't want to mess with that. So. Probably keep going a little bit, but I'm going to reheat that, and I'm actually going to put a tool holder on the guide so that I can put some stop locks in there. I want to take this down to 1 inch square. I'm a little bit heavy right now, which is perfectly fine. What we're going to do is we're going to forge this to 1 inch square and then inspect it and see if we need to do any grinding on it. And if we don't need to do any grinding, then we'll forge it to a 1 inch octagon. Now, one of the things that I'll draw your attention to, it might be difficult to see from the back, but you can see where the end has ripples in it. Partly that's due to the end not being ground or smoothed out after the bonding process, but it's also due to the fact that these different materials have different strengths at the same temperature, which basically means some of them are a little harder than the others. So the ones that are softer are moving a little faster under the hammer than the ones that are harder. So that creates a little bit of that ripply effect. It's not going to really matter much in the end result as far as the finished piece is concerned. It's just an interesting observation. So these are the stop blocks I'm gonna use. These are just 1-inch thick, nothing fancy. Whatever I had around that was 1-inch material.